This video presents the EddySonix Acoustic Resonance Testing platform for non-destructive evaluation of cast and advanced manufactured metal components. ARS means Acoustic Resonance Sweep. ARI means Acoustic Resonance Impact. The excitation methods are different, but both use the same EddySonix modal analysis framework: mode fitting, stable mode labeling, feature extraction, and database-driven decision-making. The main inspection challenge is that many defects are volumetric or structural. They are not always visible on the surface. This is important for castings, powder metallurgy parts, metal injection molded parts, and additive manufactured parts. Typical problems include cracks, voids, shrinkage, lack of fusion, low nodularity, microstructure variation, and local geometry or density changes. The production need is a fast, repeatable, non-destructive inspection method. Acoustic resonance is useful because it evaluates the dynamic behavior of the complete component. The basic principle is simple. Every part has natural vibration modes. These modes depend on stiffness, mass, damping, and the boundary contact during testing. If there's a crack, void, nodularity problem, or geometry deviation, some modal frequencies or damping values can change. The system detects this abnormal modal behavior. It is important to say that ARS and ARI detect abnormal structural response. CT, X-ray, or destructive analysis may still be used to confirm the exact defect type or location.
The platform uses two excitation methods. ARS, or Acoustic Resonance Sweep, uses a controlled piezo sweep. It is suitable for small, advanced manufactured parts where high-frequency modal information is needed. Depending on the configuration, the bandwidth can reach up to 1 MHz. ARI, or Acoustic Resonance Impact, uses mechanical impact and microphone pickup. It is suitable for large cast components, such as calipers, knuckles, and similar cast iron parts. The mechanics are different, but the data workflow is the same: mode fitting, mode labeling, feature extraction, and decision models.
This slide shows the ARS hardware concept. A preloaded piezo actuator applies a controlled sweep to the part. One or more point contact pickup sensors record the response. The sweep is not just a simple sine sweep. It is synthesized with controlled bandwidth, amplitude profile, and timing so that we obtain a clean frequency response. For small, stiff, lightweight components, high-frequency modal content is important. Repeatable contact and low noise acquisition are therefore part of the measurement method.
For large castings, impact excitation is more practical. A mechanical impact excites many low-frequency modes quickly. The microphone pickup avoids direct sensor contact on large cast parts. This is useful for cast iron components, where the quality requirement is related to nodularity or casting integrity. Changes related to low nodularity, cold shut, shrinkage, cracks, or geometry deviation can change the modal response. Temperature and part mass can also be recorded and used to compensate normal production variation. After excitation, both ARS and ARI follow the same analysis chain. The system records the response, calculates the transfer function, fits the modes, labels them, creates features, and then applies decision criteria. This common workflow is an important advantage. The same EddySonix software philosophy is used for part programs, reference databases, training, criteria, reports, and batch test. This reduces operator training and keeps the engineering workflow consistent across different NDT methods.
A key technical point is that the system does not rely only on simple peak picking. Peak picking can fail when modes are weak, close together, overlapping, or affected by noise. Also, the highest point of a peak is not always the true modal frequency. The fitting algorithm estimates modal frequency, damping, and amplitude using a physical mode model. For the final decision, frequency and damping are the main diagnostic features. Amplitude is fitted, but it is not the primary diagnostic feature. This gives more stable modal parameters in dense spectra. Multi-channel acquisition improves confidence. A single pickup can miss a mode if the sensor is close to a nodal region. Several channels help confirm real modes and reduce channel-specific artifacts. Stable mode labeling is also essential. Each fitted mode must keep the correct label, such as F1, F2, and so on. If, for example, F51 is mislabeled as F50, then the ratios and multivariate decisions become wrong. Depending on the part geometry, the useful mode count may be small, or it may reach tens or several hundred modes. The main diagnostic features are modal frequencies, damping factors, and selected frequency ratios. Frequencies can shift because of stiffness, density, geometry, or structural defects. Damping is also useful. In our applications, cracks and low nodularity often increase damping in selected modes. Frequency ratios are important because one individual mode may still be inside its limit, while the relationship between modes changes. In a good part, the modes remain in harmony. A local defect can disturb this harmony. When many modes are available, thousands of ratios are possible, so the software selects the most relevant ratios automatically. The final decision can use several layers. The simplest layer is a single variable limit. Then we can add frequency ratios, PCA, regression, classifiers, machine learning, and anomaly detection. If known defect classes are available, they can be classified. If the defect type is unknown, the system can flag abnormal behavior for review. The important point is that the output is a controlled quality decision based on a database and defined criteria. It is not black box AI. This slide shows one ARI result on cast iron parts. The training set included 200 good cast iron parts collected over 2 months. The independent test set included 500 good parts, 100 low nodularity parts, and 56 parts with other casting defects. Using frequency limits alone, the system detected all low nodularity parts, but some random casting defects still overlapped with the good population. When frequency ratios were added, the result improved. With PCA and frequency prediction, all defective parts in this dataset were separated. This result is dataset specific, so each new component family still needs its own reference database and validation. This slide shows 2 ARS validation examples for small advanced manufactured parts. In the first Aerospace Ti alloy MIM study, about 800 samples were tested. The samples were around 50 grams, and suspect parts were rechecked by CT. In this application, cavities larger than about 0.25 millimeter were detected. The second example is valve seat production testing. These are small powder metallurgy ring components, around 8 grams. The system is used in routine production for more than 2,000 parts per day. Cracks and cavities were confirmed by X-ray, and X-ray defective samples were also identified by ARS. The common output is a go-no-go decision based on frequency, damping, and database-driven criteria. In automated production cells, feeding, loading, and sorting can also be integrated. The typical sweep time is about 5 to 10 seconds.
To keep the method technically balanced, there are boundary conditions. A reference database is required for each part family. The defect must change the modal response enough to be separated from normal production variation. Also, CT, X-ray, or destructive analysis may be needed to confirm defect type or location. The conclusion is that ARS and ARI use different excitation methods, but they share one modal analysis framework. The key contribution is multi-channel mode fitting, stable mode labeling, selected modal ratios, and statistical or machine learning-based evaluation. Thank you for your attention.